Okay, so first of all, thank you for the invitation. It's always a pleasure to come back to where I became a telecom engineer. Thank you very much for this. And in my talk, I wanted to focus on that indium phosphide is not alone. It's now after having passed so long confinement, it's always good to be reminded that we are not alone. And actually, there are new technologies that are helping getting the best out of indium phosphide. So just a brief introduction. One of the main reasons why photonics is a key driver technology is because it created this paradigm shift in communications, increasing the transmission speed, the bandwidth and distance factors. And actually, this is why photonics got the place it got. And this all happened by something in the 80s, because in the 80s was when optical fiber got its low loss, and that allowed optical communications to be deployed, but also because of the development of the semiconductor laser, which allowed the direct modulation. And this was done on indium phosphide, emitting actually the windows in optical fiber. And I remark this year because actually, photonic integration is not new. Actually, this is a graph from a paper that all that we work on photonic integration used, collecting how many components were included in the indium phosphide substrate. The idea of photonic integration was initially seeded in '69. That's when I was born. And actually, this in the 80s, from the 80s, you see that this starts to evolve, increase. And actually, what you can see is there are different components that are what was needed in optical communications at that time. Around the 90s, this WDM was used, and you can start seeing that we get optical multiplexers and demultiplexers, the AWG, which is quite a complex device. Indium phosphide was not the only material used. Indium phosphide is always used for when you need to generate light. That's what we know. If you need light, there is nothing more efficient than indium phosphide. However, there were other materials that were already used. The main one was glass, because actually the AWGs were better done in glass because it had lower losses. And actually what we had was a competition between different materials. Today we have indium phosphide together with silicon photonics, silicon nitride, polymer. All these materials seem to compete on different functions, because actually what we get in our chips is functions. And you want to get the best performance, so you go to the material that gives you that. And actually today, one of the best materials that we have for passives is silicon nitride, because extremely low loss. And I will show you a bit on polymer. This is a line that I had to add in this table, because actually polymer is extremely good for high frequency, and we need that. Why we need that? Because there is a paradigm change again in communications, and we are on mobile communications, wireless, if you want. And what we have is that our network is not just optical. This is the part that was developed, optical wire communications. And today our networks are going mobile, and what we have is remote radio heads. That's what we call the front haul. And the front haul is how you communicate with mobile devices. And in mobile devices, with 5G communications, what the networks have been going is to higher frequencies, actually because most of the wireless communications were done at lower frequency, below 6 gigahertz. This is Wi-Fi wireless. Actually, all our towers work at below 6 gigahertz, these remote radio heads. But there is not enough bandwidth to get the speed we need in our terminals. So 5G is now considering is not some tests have been done on 26 gigahertz, and that's the maximum frequency is considered. Because actually, when you start thinking about with photonics was okay. If something has photonics in it, it's going to be expensive. It's like going to a restaurant and getting served before you have lunch this hot towel to clean your hands. You start saying, okay, I'm going to be rip off. That was the feeling of photonics. Now photonics has gone in optical communications, has decreased the price. And now the problem is in frequency, high frequencies. When people think about beyond 6 gigahertz, they think, oh, that's another world. It's going to be a ripoff. And actually, at higher frequencies, it's the only place where you have amount of bandwidth. And that's where we need to go, actually, to establish the links beyond, because actually you see, as we go higher in frequency, throughput, number of data is increasing, but coverage is decreasing. And this is because of absorption and because of mainly absorption. And problem is what we do with this. Actually, what we need is we can use this to actually increase for 5G. Actually, people is thinking, okay, we need to increase the density of our network. We need what it's called small cells, and these small cells can be connected through high frequency wireless connections, so that will help the deployment. And this is where high frequencies are coming in for bandwidth. The another additional challenge is that today we are at these low frequencies. Low frequencies means you have very wide coverage and you spread your signal around. And in 5G, what we are moving, one of these, this is an advantage because you don't need to know where your device is. You will always be connected. As we move to higher frequencies, increasing loss, okay, we can concentrate the energy on a small beam, and this will make the system more secure and actually more energy efficient, greener. That's one of the things is looking for today. So we need phase arrays. Phase arrays will allow you to do beam forming, that is, make this as narrow as you want, and beam steering to actually look for the device where it might be. For this, we use arrays, and in arrays, people are usually thinking in optical because of the smaller wavelength. It actually means everything is smaller, more compact, bandwidth, and in microwave photonics, we are in the best of both. We use the wide bandwidth of photonics, but actually the problem of the optical communications is that it's the alignment of the two terminals. Because one of the problems is that with a smaller wavelength, you are more sensitive. Well, we have seen now, you are sensitive what the atmosphere does, and you have what is called beam wander. And depending on the heat in the path, you may lose the sight. So that RF has advantages. And actually, this is what we are looking at. We are actually developing these devices for 5G communications, in which we use all the signal is in photonics. We take advantage of the wide bandwidth, and you just convert it to the RF where you need it, at the antenna. And the same thing in the receiver. And this is actually blending RF into photonics and the other way. And this is what is called microwave photonics, which is the perfect marriage of these two technologies. Actually, you see, we have ultra wideband, because photonics basically gives you infinite amount of bandwidth, infinite, in terms of what we are used to in RF. It's ultra broadband. You can use any frequency. You can actually have reconfigurable systems, because we have seen we can tweak with the lasers. It's reconfigurable. And I will show you how we are achieving beam forming and beam steering. challenges that we have is that, okay, we have to integrate many different components together because we need optical signal sources, modulator amplifiers, signal processing. This means, okay, I cannot have the best of everything because I showed you before that silicon nitride is good for passives, indium phosphide for the actives. And also that we are not just integrated microwaves and photonics, it's also electromagnetics when we want to emit this signal. This is our challenge. So I'll show you a bit what we've done. For the generating high frequency with optics, we mainly use optical heterodyne. Is a technique in which we beat two wavelengths in a photodiode. So we generated the difference frequency. And our first thought was, okay, let's put everything on a chip. There cannot be anything better than having everything on a chip because then optical path lengths, well, the chip will suffer the same. And this is what we did. The chip will be on the same substrate, one Peltier, same temperature. We will sort of solve the differences that having the two lasers on a different package may bring. We did this in 2010. Project started in 2010 and ended in 2013. Actually, this was more at the end. And we integrated all of these elements together. And with this, we actually got 1 megahertz line width. First thing we noticed, oh, we don't get anything better than what we have when these are on separate packages. We get the same DFB laser that you get in any substrate, whether they are together or not. We were achieved to tune this. This is the optical wavelengths that we are beating, and this is the RF that we are generating. And as you can see, we did it with thermal tuning. Actually, it's with current. We're changing the current, and we get different amplitudes, and we get thermal cross-coupling of the two because we're close together. But we generated different frequencies. This is an offset of 90, so this is starting at actually this was 95 gigahertz up to 100. Basically, we got what we wanted, but this required a very complex integration. This was it's an indium phosphide, and we integrated DFBs. This is the DFB grating layer. This is the grating layer. If you remove this layer, we actually get the SOAs. In the passives, this required a new regrowth, and photodiodes needed another regrowth. This was a two regrowth fabrication process that started off with the passive. You had to regrow the active layers and then the photodiodes. Extremely complex. And I'm not going to say this is once on a lifetime chip, but it's extremely expensive to fabricate. So we looked around and we thought, okay, actually, do we need it? We thought about it. Do we need it? Because actually, if we want to put this into the radio head and this is going to be in the base station, why do we need to integrate all of this in a chip? So we were starting to think a bit more cleverly than just the challenge of putting everything together. And then we looked at hybrid integration. And hybrid integration, we've looked at polymer, because this is the polymer platform from HHI. And in here we have DBR lasers. And very recently, also, Lyonics International also showed that they had extremely narrow lasers on silicon nitride because they use high Q resonators, which allow you to fix the wavelength very much. We actually use this to generate RF, beating the two wavelengths of these lasers. Actually, in each of these chips, there are two lasers integrated together. And as you can see in polymer, we actually get same line width that you expect on a DBR. Tuning range was huge. That was amazing. And problem was that it requires thermal filters, which sometimes is too slow if you want to scan in frequency. we moved to Lionics, and we actually got what we expected, very narrow line width. This is the electrical one. So this is the bitting between the two. And actually, the tuning range is good enough for us. Again, thermal heaters. Well, let's see. Well, it's what we have now. We have to develop this. I'm going to show you a bit what this laser looks like. It's an indium phosphide. Indium phosphide is anywhere you want to generate light. So this is a hybrid integration between indium phosphide and silicon nitride. Indium phosphide is for the gain, silicon nitride for the passives. Is the best actually is the best solution for photonics to generate. Use the best of the active for generating light and the best of the passive to actually do the optical filtering. Because actually, you can see here, these are the optical mirrors, which are ring resonator mirrors in the passive. And this is the silicon nitride, and you can see here the two gain chips. Actually, the gain sections are in two different gain chips. We actually show this is the optical spectrum. You can see, since the chips are in separate gain chips, we don't have any thermal crosstalk. When we tune one of the lasers, we get that one laser being tuned. This is the bitting between the two, and this is these are the optical line width and the electrical line width. And we are actually scanning through 70 to 110. This is just to show you a frequency range that we are interested in. What is the advantage of silicon photonics? That actually Lionics already has an optical beamforming network to actually point the beam. What is the problem that we highlighted to them? Is that you still have, this is where the photodiode, this is where the two lasers are, the optical beamforming. Actually, you have here the modulator and the photodiodes. They did the same thing we did, put everything on a chip. But here you have the RF out. And this is what you want to avoid. This is where you want to put the antenna. Because cables, coaxial cables, has high loss. That's what photonics are for, to take the signals where you want, and then you convert. This is what we want. We want to put as many components, the components that we need for the base station, optical fiber, and then the radio head. And in the radio head is where you put your optical beamforming, so the phase difference between the different paths doesn't change. You put your photodiodes and your antennas, and you emit from them. Problems. How do I connect my antenna? Because that's where I have high frequency. Today, you can use rectangular waveguides. Problem is bandwidth limited. So the problem, I have a huge bandwidth photodiode, then narrow down. This is like going on a 3-4-way highway and then getting to a one line. That's a bottleneck. And actually, you have to throw everything away if you need to change the frequencies. The other option is silicon lens. Then you have a wide bandwidth antenna. This is a planar antenna on the photodiode. And still, the problem is that the radiation goes into the substrate, higher refractive index. And how do I collimate this? Because at the end, I want to have a beam with a phase front. The only option is silicon lens. Very expensive, few people that fabricate this, not a good idea. So what have we done? Integrate the antennas. Actually, we are developing, this is indium phosphide with the antennas. This is with edge coupling. And we have actually used this to increase the emitted power, wide bandwidth. Problem is that we have 1D array. It does beam steering, so you can steer the beam. But the problem is that it's in one direction. And you have to rely on this RF substrate to get an efficient emission. Then we found out, polymer. Polymer is an extremely good substrate that gives you high gain antennas. So that's actually quite interesting because there is a photonic polymer. If you can use photonic polymers and do the antennas on the polymer, that would be great. It's even better because, well, I show you that we have these lasers where we can generate RF, but you have optical isolators in polymer. So we're thinking, it's not only silicon nitride that we need to include polymer. That's what we are looking at. And then finally, for the antennas, because I saw you, okay, the antennas on that I saw you before, it's 1D. What happens if we want 2D? Because people are thinking about 2D. Even we are thinking on 2D. If you want 2D, the problem I show you is the silicon lens. How do we get rid of the silicon lens? Because silicon lens basically collimates. That means you cannot steer. Well, what we have come up with is the electric rods. These dielectric rods are the way to convince radiation to get out of the material and still be collimated. But the thing is that you can put huge amount of them, and you will be able, each emitter will be emitting a perfect phase front, and you have a ray, because all of these are close enough so that they work as one. They are coherent. And actually, these are the simulations that we've done to demonstrate that you can beam steer at different frequencies. And this is what we are doing within a European project. We are actually developing the antennas in this Teraway project, which it's 2 years now running. Of course, we're going to need an extension. And this is where this technology is being developed. And just to summarize, this is what we think that hybrid integration is going to be a key technology in the future. Silicon is a fundamental part, but it can we can get systems with high performance if we combine it with different materials. And for this, we're thinking, okay, indium phosphide is good for gain, silicon nitride for the passive. Actually, RF signal processing on chip can be done on silicon nitride because high Q allows you to have narrow bandwidth. Polymer is extremely good, allows you to have optical isolators. That's nothing, no one else can give you that integrated so far. And for silicon is what we think about it is to use it as millimeter terahertz waveguides, basically to get the radiation where we want and get away. Thank you very much.
Thank you very much, Guillermo. And now it's time for questions. Any question in the room?
Sorry? Oh, the packaging. That's that's a good question. Actually, this we are doing ourselves. In the project is being done by FIX because they actually have the responsibility to assemble the whole chip. So we've been discussing with them how to assemble, and they have developed an automatic assembly that now we need to think about. It's good for one, now we need to think of for many. But this is something that we did on our own. And this is something that we are doing, is we are developing this in our own. Actually, the problem here is that when you go to high frequencies, wire bonds are not usually the best option. And we've developed this with epoxies, but right now we are moving this to waveguides on polymer, and we are aiming to develop a flip chip process for this high frequency interconnects. And this one was done by HHR. And right now, actually, there are different, this is in metal, but actually right now, one of the things that why silicon is also used is because you can do all this, all the rectangular waveguide etching on silicon, metallize, and then you have perfect rectangular waveguides. we're still, we have colleagues that do this in Navarra.
Any other questions?
Thank you for your time, Paul. Are you trying to do the steering in 2D or only 1D?
We're trying to do both. We are trying to do both. The 1D is in these linear arrays with these are Vivaldi antennas. Now we are developing also linear taper antennas, and these arrays we are thinking of for 1D. We have this is a line of work because it's easy to get to put our photodiodes in an array. And you always can use the edge of the chip for this. So if you need only one direction of the steering, it's okay. And we are also developing this. Actually, this is an antenna array in which this is a complementary antenna. It's called chessboard array, and you actually put the active elements in the tip of the antennas. So actually, when you bias you don't bias the top and the bottom. You can actually bias each line. So any defective component, if you have a defective component in high voltage in one of these, it will probably concentrate the current and will burn. And when you do these structures, you actually can bias them in the lines independently, and you don't need to get too many, because the problem of the arrays is that you have to get too many metal lines in a small space, and this simplifies the interconnectivity besides allowing to bias them separately. And with this, this is where the rods come in. And this allows you to get the RF in. And now the only problem is to get the light in. So you have to actually plan for your input waveguides to each of these elements. But this is the approach that we are using.
How many delay lines you need for this to be
actually, you need optical beamforming network of the same dimension as you have. In this case, it's 9 elements. So you need 9 delay lines. Currently, they are using 4 lines.
Okay, thank you. Any other question?
The presentation. I'm just wondering how you're going to tackle the problem with the switching factors, because you mentioned you're using 10 months tuning.
Yes. That will always depend on what you want your steering for, and that's why when I presented our application, is not to search for the device, because if you need to search for the device, you need to point for a person going in a car. The extreme is that the Japanese are doing is people going into a bullet train. Our aim is to be able to do this steering, because when you do a small cell deployment, you fix the cell, but you need to have some control of the steering, because you will never put the cell actually aligning to the tower cell. So what you want is to have some steering here, so you can freely deploy. You have one design of the small cell, you put it, you search for the position, you align it with the tower cell, and then you need a small steering in case if there is any wind or you have drift because of the wind, but not high speed. So we are looking for solutions that for us, this works. And if we, I don't think we will never need to track a device, because the bandwidth here is not, doesn't justify millimeter waves. I know that the latest iPhone has in the US has a millimeter wave port, but this is also for you know, this they call it this multimedia kiosk, where you download a movie really fast, and then you can fix the device in a position that it's already aligned, and it's fixed. So we are not looking for connecting to a device directly with millimeter waves. How we avoid the problem is not looking into it.
Thanks for very much. The phase delay that is actually introduced in your lines, how big is it?
Well, that's right now. You know, one of the things is that you have to delay the data. So you need, depending, that depends on the steering angle that you want. And right now, I hope now we have this external optical delay lines. We are not, so we have plenty of delay, and we are using this because so far we have not put together all the building blocks that we want.
Concerning the 2D antennas, yes, we are in the VISTA project. This is a project about 3D imaging, but also LiDARs. And we have some developments in automotive LiDARs. And in the last time, there are very impressive results when people have 2D fixed and OPA antennas. Yes, this is exactly the same. So maybe this would be the direction when you are working with your.
There are many people that are going to this type of antennas. This is the leaky wave antennas, and the advantage of this is that well, advantage. To steer here, it steers in one dimension, and you steer with different frequency. So it's you need to change the frequency, and when you change the frequency, you change the direction. And actually, you can actually steer in 2D if you put an array, if you put multiple antennas. Yeah, and with leaky wave antennas, you can do that.
And now they have like LiDAR chips. So really a lot of lasers, detectors, and also OPA.
Yeah.
Because then you going with the car, you need to scan kind of area. So
yeah.
The idea
in our approach is that actually, and this is things that people need. If here you need narrow data, you have to have a high complex modulation, because you need to narrow the bandwidth that you occupy with your data, because otherwise your data, depending on your bandwidth, will go in different directions. So you need to narrow it down so it doesn't spread. That's one of the disadvantages of this. For LiDAR, if you don't, you usually don't modulate over a wide bandwidth. So that's okay for bandwidth. And in some applications, you need to fix the frequency. So you cannot freely dispose of any frequency to put to do the steering at the position you want. The bandwidth, the frequencies are fixed, and you have to stick to it. And our solution is, okay, let's make it independent of the frequency.
Okay. Have you actually questions? Yeah.
Oh,
What was running at heart is the material for polymer hybrid integration. Is there any requirements regarding the material processing, like photopure versus thermopure material?
In actually in polymer, it's another advantage of the polymer. It's a fabrication. It's not complex fabrication. It's very simple fabrication. It's a spinning and curing. So, and it requires. It's one of the advantages they claim. It's a lower complexity fabrication. And the problem of putting all together is the assembly. A hybrid integration is not picking up faster because when you need to, I'll go to one of the pictures, for example. Well, this is good. Yeah, when you need to do the optical alignment of different chips, this is understood. This is a quite very complex process. It's time consuming. You have to do it one by one. And this is why hybrid integration is not seen as a solution for volume manufacturing. And that's something that I guess we are thinking how to address this problem. But so far, by the people doing the packaging, they claim they can do. This is an automated process. They are developing automated steps. And
Okay, thank you very much.
I could to give them more, but time is limited.
Okay.
Thank you very much.